Okay, this is the SIA 821 January 2010 question on civic heat capacity. So in this question it's talking about heating up milk and its container. So obviously we know civic heat capacity equation is the energy given is equal to the mass of what we're heating times this constant of heat capacity times the change in temperature. Now also realise that a change in temperature in Kelvin is going to be exactly the same as a change in temperature in degrees. So for these values here, you do not need to turn them into Kelvin. Okay, so in this experiment we have 240 grams of milk. Now, the mass is in grams. If we have to keep it in grams or change, we need to look at the unit. So the unit for civic heat capacity is joules per unit kilogram. So we have to turn this mass into kilograms. So obviously you can divide it by 1,000, or you'll just know the mass. I'm putting a wee small m here to show that is relating, that mass value is relating to the mass of milk, is 0.24 kg. Okay, it is heated from room temperature in a container of mass 75 grams. So that is a different mass, and this is for copper. Again, it's going to have to be in kilograms. So I'm putting M for mass, putting a wee c beside to show that's the mass for copper, and it's going to be 0.075 kg. Okay, and then it gives us the actual civic heat capacity value of copper. So I'm going to put the c beside that and a wee small c to show that's related to copper. A small electrical heater is placed into the milk. Okay, so what's going to be happening is this heater is not only going to heat up the milk, it's also going to heat up the container that it's in. So if you put something in the microwave or even in the oven, it's not just the food or the liquid content that heats up, the container that it's in also heats up. Okay, so in this question the energy supplied is going, the energy in is going to equal to the energy of given to the milk plus the energy given to the container, which in this case is made of copper. So we have the potential difference across the heater is 12 volts, and the current here, so I'm going to put I, and the heater remains on for 6 minutes and 50 seconds. Now in regards to this, you're saying, well, this equation does involve current, voltage, or a time, but energy is equal to power times time, and electrical power is IV, so it's IV times T. So I can just put in my values for voltage and current, they're fine. So 2.6 multiplied by 12. Now the thing about the time is time has to be in seconds, so you have to convert your 6 minutes into seconds, which is 360 plus the 50, so what's that, 410, and if we multiply them together we'll get the total energy supplied to both the milk and the container, the copper container. So that equals 12792 joules. Okay, during this time the temperature of the container and its contents, so the copper container and the milk, increases by 13 degrees. So this has given us the temperature change, and both the copper and the milk change by the same amount. Okay, calculate the civic heat capacity value of the milk. So what I said before, this energy here is the energy given when we put it the wee heater into the milk. The total energy is equal to the energy given to the milk plus the energy given to the copper container. So I have my total energy in, because I've calculated that. It is 12792, and it is equal to, now I'm going to put in my values for civic heat capacity. I'm going to write that equation first. So it is the mass of the milk times the heat capacity value of the milk times by the change in temperature of the milk. In this case, both copper and milk changed by that amount, plus the mass of the copper, so the heat capacity of the copper, and the change in temperature of the copper. So now I'm going to start putting in my values. So When you're going through a question, please be aware, just underline things, give it a value. So when you're going to do your calculations, you know, well, that's the mass for the milk, that's the mass for the container, just so you don't get confused. So I'm going to put in 0.24 multiplied by this. We want to find the specific capacity of the milk. That's 13. Plus the mass of the copper times this value here, 0.39 times 10 to the power 3 times 13. Okay, so what we technically have is we want to get the energy just given to the milk. So to get that, we're going to multiply these values together, and we're going to take it away from this side, and if we take it away from this side, we're going to take it away from the other side. So when I do that, I am going to get 2 more. Okay, so all I've done there is I've multiplied this here out, and to get rid of this, because I want to focus on purely the milk, I've just taken this calculation when I multiplied it out away from each side, and I'm left with this. So that's my energy now given to the milk. So the energy given to the milk is equal, so it's basically energy of the milk is equal to the mass of the milk multiplied by the specific heat capacity multiplied by the change in temperature. Okay, so just to get it over, I'm just going to multiply 0.24 by 13 and then divide it to get the specific heat capacity value for milk. And when we do that, you should get about 3.978 times 10 to the power of 3. Okay, and that's your answer.